Hey everyone, and welcome back to this class. This lecture is about how to write code independently when you're doing machine learning. You always hear me say that the first thing you should try to do when you learn an algorithm is to go and write it up in code by yourself before looking at someone else's code. For some students who are new to machine learning, it's not quite clear how to do that. So this lecture is going to explain the thought process you should go through in hopes that it encourages more people to try to code by themselves. I like to encapsulate this in the phrase, when it's time to code, you must code. So remember this whenever you see some code that demonstrates the concepts we learned in this course. Even if you don't fully understand what's going on, coding and copying examples from others helps you build muscle memory. Sometimes people act like they are going to learn tennis by reading a book about tennis. This is of course obviously not possible. You need to learn some things about tennis which are pure fact and reside in your brain as conscious facts. But then you have to go out and practice those concepts on the tennis court. Once you've exhausted and mastered everything you know so far, then you can learn new techniques. So you have this continuous cycle of learning new techniques and then practicing them. Why is this? Because learning the technique as pure fact doesn't mean you truly understand it. Practicing the technique helps you think about the technique from a different perspective. Practicing again and again leads to new understanding, to learning in the subconscious, which is muscle memory. You must go through this cycle. But some students naively think they are going to read an entire book about tennis and then be a tennis master the first time they try playing. This is very common, especially when all you really need to do is sit there and watch a video and no one can force you to type. A lot of people don't even think to try. So just remember this whenever you see code. When it's time to code, you must code. First, we are going to talk a little bit about why you want to code by yourself. A lot of the time, what an algorithm does or how it works isn't quite clear the first time you learn about it. Every individual will have their own unique background, so they might be familiar with the patterns and know exactly what to do, while some individuals might have questions that no one else has. Sometimes you gloss over details because you assume you know what's going on, when really there are important things you're not considering. So this is how trying to code by yourself can help you. Coding by yourself forces you to think about each and every detail. It forces you to think line by line. You have to be familiar with the data types and the shapes of all your variables, and they all have to fit together properly, kind of like Lego blocks. As an example, you know that in order to do element-wise matrix addition, both matrices have to have the exact same shape. So if you find that they are not the same shape, then one of your previous assumptions was incorrect. So you should go back and correct it. Lego blocks have to follow a specific set of rules in order to fit together properly. If you make incorrect assumptions about how Lego blocks fit together and you try to join them, it's not going to work. Without trying to build things by yourself, you will never discover these details. Let's now talk about how to code by yourself. Consider the supervised machine learning scenario. We know that we're going to have some inputs and some targets, and we want to try to make predictions from the inputs that are very close to the targets. We typically call the inputs X and the targets Y. Sometimes we call the targets T, but for the purpose of this lecture, we'll call the targets Y. Now this next point is a key point. It doesn't actually matter what X is and what Y is. It doesn't matter if you're looking at an e-commerce data set, and the columns of X might be time on site, time of day, how many pages the user looked at, and so on. You could just as well be looking at a data set of X-ray images, where each column is the pixel intensity of an image. This is the key point. We say all data is the same. When we do linear regression, we don't have different kinds of linear regression for e-commerce and X-ray images. Linear regression is the same algorithm no matter what your data set is. So we say all data is the same. Theoretically, I could give you a data set of X's and Y's, and you could train a classification algorithm on it without me even telling you what the X's and Y's mean. You should get very comfortable with this idea. Sometimes people say, well, this isn't practical because I want to do concrete examples, but that's because they're not thinking intelligently. In fact, this is the most practical thing we can do because it means everything we learn, we can apply it to any dataset that exists. It means that I can train a model on an e-commerce dataset, but I can also train a model on an online advertising dataset without learning anything new at all. It's truly the greatest form of lazy programming. Learn something once and apply it to every industry. One great consequence of all data is the same is that there is an unlimited amount of practice opportunity for you. You can download datasets from Kaggle, from Google, from Wikipedia, from Amazon, or from anywhere else and try the algorithms you learned. What this means is, let's say you have a dataset you care about more than something we do in class. See, in class we have to use datasets that everybody can understand. For example, text and images. Everybody should know what text and images are. Text and images are just fundamental data types on the web. You probably don't even think about the fact that text and images are data because it's so trivial. In any case, we work with text and images a lot because everybody understands them. But let's say you're a biologist and you know about DNA. You find DNA and genomics really interesting. So you want to use the algorithms we learn on that. Well, that's great and you should totally do it. Remember, all data is the same, so all you need to do is convert your data into the appropriate X's and Y's to plug into our machine learning algorithms. The downside is, we most likely won't talk about DNA in class unless it's a very simple example, because most computer scientists are not biologists too. So they don't know what DNA is. They don't understand the specifics. So an example wouldn't make much sense to them. This is opposed to text and images, which makes sense to everybody. Same goes with any other specialized field like finance, computer networking, cosmology, and so on. So now we can start off from the right place to talk about supervised learning. We have our X's and we have our Y's. What do we do with them? In supervised learning, we know that there are two main things we want to do. We want to do training and we want to do prediction. In scikit-learn, all the models have the same API. It doesn't matter if you're doing logistic regression or decision trees or random forest. All supervised models in scikit-learn have the same two functions, fit and predict. Fitting a model is just a synonym for training a model. If you don't believe me, you can go look at the scikit documentation yourself. When you're learning about supervised machine learning, what you're really learning is what goes inside these two functions. What are the parameters and how are those parameters learned? That's really what all supervised machine learning is, filling in these two functions. Taking this perspective is going to give your code structure and it's going to make things much easier to visualize in your head. Let's now do a simple example to solidify this idea. In this example, I'm going to give you an algorithm and you will implement it in code. There are two key points I want to make before I give you the algorithm. First, I'm not going to give you much intuition about how it works. Second, I'm not going to derive the theory behind why it works. The reason I want to mention these two key points is that you should realize you don't need these two pieces of information in order to translate pseudocode into code. A lot of time, these three concepts, intuition, theory, and implementation, work to reinforce each other. The reason I'm focusing on implementation right now is because it's the one people most often miss or think they don't need at all, when really it's an extremely important part of the learning process. Okay, so the pseudocode is as follows. In my predict function, as you already know, I'm going to take in some input data x. My predictions will be y hat equals x times w. You might already recognize this as linear regression. However, forget what you know about linear regression and pretend that this is just some formula I gave you. What I can tell you is that we are creating some kind of regression model. It should be clear from this equation that the parameters of the model are contained in this vector of weights w. I would probably also tell you that w is a vector that's the same size as the number of feature vectors in X. Of course, this must be true in order for the matrix multiply to be valid. This acts as kind of a sanity check so you can make sure everything is making sense. In my fit function, I want to perform this loop some number of times. Since we know from the previous slide that the parameters of the model are contained in W, then it should be clear that inside the fit function, what we want to do is update W. Not surprisingly, that's what's happening here. Another good sanity check. Now, because you're already familiar with linear regression, you probably already recognize this as gradient descent. Again, I want you to pretend that you don't know that. But what do you know? You know that iterative algorithms are common in machine learning, and that gradient descent is among the most common. You could probably infer that this is some form of gradient descent, but you don't need to know what it is in order to write it in code. What else do we know? You know what a for loop is, and you know how to write one in Python. You know that X is an n by d matrix containing the input data, and that Y is an n-size vector containing the targets. You know that Y hat is an n-size vector containing the predictions. You know that W is a d-size vector containing the model parameters. And you know how to add, subtract, and multiply these objects. So we can write this algorithm without even knowing how it works. Of course, a lot about how it works can just be inferred from this formula. Here is what you don't know. You don't know t, the number of times the loop is supposed to run. You don't know eta, the learning rate. This is completely fine. You can't let this lack of knowledge stop you in your tracks. The truth of the matter is, there are going to be situations where you're not told the exact numbers to plug in. In many cases, the answer is going to be, it depends on the problem. The important thing is, you have to get used to the idea of trial and error, and you have to make educated guesses based on what you already know. So what can you do? Well, you know that the learning rate is supposed to be a small number. How small? It depends on the problem. Typically, it's a number less than 1, like 0.1. If that doesn't work, you might try lowering it. Typically, we lower it by factors of 10. So for example, the next learning rate we would try is 10 to the minus 2, 10 to the minus 3, and so on. Typically, in machine learning, whether you're looking at a supervised or unsupervised algorithm, there is an associated cost or objective function that you're trying to minimize. Let's suppose I tell you it's squared error, which is typically what we would use for regression. Well, now you have a way to choose the number of iterations of the loop and the learning rate. How do we do this? So inside your fit function, you would plot the cost as a function of iteration. I always recommend doing this, no matter what algorithm you're looking at. In general, you always want the cost to converge. The pattern you typically see is that there is a steep drop at the beginning, and it slowly flattens out as the number of iterations increases. To choose the number of iterations, you want to stop when the curve is sufficiently flat. You might recognize this as a diminishing return scenario. The returns diminish because at the beginning, we reduce the cost by a lot in just a few iterations. At the end, we can do a lot of iterations, but we reduce the cost by almost nothing. An alternative is, you could use a separate validation set and stop when the validation cost increases, but that is not the focus of this lecture. Unlike the training cost, the validation cost is not guaranteed to decrease at every round, because that is not what we are minimizing with respect to. You can also use this same plot to help improve your learning rate. If the cost explodes or becomes not a number, your learning rate is probably too high. If your cost converges too slowly, you can try increasing your learning rate. So what does your final code look like? Well, we know we want to create a class with at least the predict and fit functions. You don't have to use a class, but I find that it encapsulates the code nicely and provides useful structure. Notice that once you have the algorithm in math, there isn't much work to convert it into NumPy code. You know how to do matrix multiplication, you know how to add, you know how to subtract. These are basic arithmetic operations that I'm sure you know already. If you don't know how to do these in NumPy, then I have a completely free NumPy course on the NumPy stack that you can take. Here is the second part of the code where we actually create an instance of the class and then use it. I've also included the squared error cost function just for completion's sake. What's cool about this template is that it doesn't really change from one algorithm to the next. The structure is basically always going to be this way, at least for supervised learning and unsupervised learning. So as we discussed before, it doesn't matter what algorithm you're implementing, whether it be linear regression, logistic regression, a neural network, and so on. They always have the predict function and the fit function. And learning what goes inside these functions is equivalent to learning the algorithm. So in fact, one way to begin coding is to start with just this boilerplate code and then fill in the blanks.